So first, I want to begin by noting that it is a distinct honor and pleasure to be giving this plenary talk. Of course, we all wish we could be together in person, but I want to thank the conference organizers for putting together such an excellent virtual conference. And thank you all for attending my talk virtually. I look forward to meeting up with old and new friends in person sometime soon. My name is Sam Coogan, and I am an assistant professor at Georgia Tech. My talk today will present some recent and ongoing work in my group focused on obtaining formal assurances of dynamic and autonomous systems using new tools from reachability theory. I'll begin by giving a brief overview of the research in my group. Broadly, we develop formal theory and tools for establishing correct or desirable behavior in control systems. We're often motivated by applications in transportation systems, and we've applied our work in domains including complex traffic networks, multi-agent distributed control, formal methods such as model checking applied to control systems, and applications in safe autonomy, which will be the focus of today's talk. Before outlining the rest of this talk and presenting our main work, I want to briefly recall the topic of reachable sets for dynamical systems. Consider a dynamical system with vector field F that is a function of state X and an unknown disturbance W. Reachable sets characterize the possible evolution of the system state over time. For example, with initial state x1, the dynamics might arrive at state x1 at time t after time horizon t. Moreover, the same initial state x1 might arrive at a different final state x1 prime of t because of the unknown disturbance. And of course, a different initial condition will arrive at yet another final state x2 of t. If we consider a set of initial conditions in all possible final states over time horizon t under all possible disturbance inputs, we call this resulting set the T reachable set for the system. It is generally quite challenging to compute exact reachable sets, and therefore we are often interested in obtaining an approximation of the set. Here's an example of an ellipsoidal over-approximation of the reachable set. In this talk, we will focus on over-approximations because of their usefulness in establishing safety and liveness properties subject to disturbances. So for example, we can verify the T reachable set does not intersect some unsafe set by confirming that its over-approximation does not intersect the unsafe set. Likewise, a sufficient condition for all states within the T reachable set to reach a target region is for the over-approximation to be contained within the target region. Lastly, we recall the related notion of robustly invariant and attractive sets. A set is robustly invariant if the reachable set S never leaves S for any disturbance, and informally, a set S is attractive if all trajectories eventually approach S. So as we see in this figure, a robustly invariant set requires that the vector field be pointing inward to the set, regardless of what the disturbance input is. When evaluating the appropriateness of methods for computing reachable set approximations, speed is becoming an increasingly important factor. In my research, we focus on computational speed for two different applications. First, formal methods applied to control systems often relies on computing finite abstractions of the underlying system, so that appropriate automata-based algorithms are applicable. In that context, it is often necessary to compute reachable sets from each region of the finite abstraction. Even low-dimensional systems might require hundreds of thousands or even millions of discrete states in the abstraction, which calls for fast reachability algorithms. My research group's ongoing efforts contribute to this line of work, but I won't have time to talk about this in today's talk. Separately, many algorithms for achieving safe autonomy require reasoning about the future evolution of the system, which often calls for on-the-fly reachable set computations. This will be the application focus of the methods we discuss in this talk. Unfortunately, the challenge is that, except in special cases, such as linear systems, methods for approximating reachable sets generally suffer from the curse of dimensionality and can become computationally intractable, even for systems with more than just a few state dimensions. In the first part of this talk, I will introduce a broad class of nonlinear systems called mixed monotone systems that are amenable to efficient reachable set approximation. In the second part of this talk, I'll show how reachable sets and invariant sets are computed for mixed monotone systems by embedding the dynamics in a larger monotone system, which allows us to leverage the rich theory of monotone control systems. In the last part of this talk, I'll demonstrate how these methods enable safe autonomy within the loop reachability on a few applications, including multi-rotor aerial vehicles and spacecraft. These algorithms will use the theory of control barrier functions. Before defining mixed monotone systems, we'll review the class of monotone systems. Consider the same dynamical system with disturbance as before. Throughout this talk, we will assume that the state space X and the disturbance space W are hyperrectangles. We denote by phi the state of this system at some time t with initial condition x0 under some disturbance signal W. The system is monotone if, for any two ordered initial conditions, x0 and x0 prime, and any two disturbance signals, W and W prime, that are also ordered for all time, the state remains ordered for all time. Here, we define two vectors to be ordered if it is ordered along each coordinate. That is, we consider monotonicity with respect to the standard ordering. Therefore, monotone systems maintain a partial order of states under the system dynamics. The definition of monotonicity can be generalized to other general partial orders, and in this talk, we will consider such a generalization for a particular southeast order, which we will define later. An equivalent infinitesimal characterization of monotonicity can be given in terms of the partial derivatives of f. In particular, the system is monotone if and only if each off-diagonal entry of the Jacobian matrix del f del x is always positive. This is the first condition here on this slide. The second condition is that the partial derivative of each fi with respect to each wk is always positive. The monotonicity property implies ordered dynamic behavior that provides tools that can be used, for example, to study equilibria and their stability. Listed here are some of the researchers that have developed the essential tools over the years that we will be leveraging in this talk. Mixed monotone systems are most easily defined by generalizing the infinitesimal condition of monotonicity. The same system as before is mixed monotone with respect to a certain decomposition function d if the following condition holds. First, note that d takes twice as many arguments as the vector field f, and it's required that d recovers f if the pair x and w are duplicated in the arguments of d. This means that d contains all of the information contained in the original vector field. Next, we require that the partial derivative of di with respect to each xj be non-negative whenever I is not equal to j. This is reminiscent of the condition on the previous slide for monotone systems. The third condition is that the partial derivative of di with respect to x hat j is non-positive for all ij. And the fourth condition is that the partial derivative of each di is non-negative with respect to wk and is non-positive with respect to each w hat k. D is called a decomposition function for the system. Note that this definition generalizes monotonicity because the conditions for monotonicity on the previous slide are recovered if we define the decomposition function D to be equal to f evaluated at the first pair of arguments and simply ignore the second pair of arguments. Two natural questions arise from this definition. First, how general is the definition? It will turn out to be quite general, but the usefulness will depend on the choice of D, which is not unique. Second, how can this definition be used for reachability and safety? In the second part of this talk, we will see that we can embed these dynamics in a larger monotone embedding system. Before we move to the second part of this talk, though, let's consider a simple example that in many ways is a canonical demonstration of how the decomposition function in the definition of a mixed monotone system decomposes the dynamics into increasing versus decreasing, or you can think of them as cooperative versus competitive effects. Consider the generalized Lotka-Volterra model, where the rate of growth or decay of the population xi of each of n species is given by the product of the current population xi with a weighted combination of the population of the other species with weights cij and possibly an offset term wi. The sign of Cij captures whether the species are in competition or cooperation. If it's positive, the species are in cooperation, and if it's negative, the species are in competition. We can then construct the ith component of the decomposition function by setting it equal to the ith component of the vector field, except we exchange xj with x hat j whenever species j is competitive with species I. In this way, this particular decomposition function separates the competitive and cooperative effects of the dynamics. Now we turn our attention to the next part of this talk, where we consider using the mixed monotonicity property to compute reachable and invariant sets. The key technical tool is the embedding system with 2n state dimensions, defined as shown here on the slide. Recall that the set of disturbances W is assumed to be a hyperrectangle. This means it is defined by a lower point, W underline, and an upper point, W overline. The vector field of the embedding system is denoted with E. The first n components of the vector field are defined using the decomposition function as shown using the extreme values of the disturbance set W. And the last n components are defined similarly, except pairs of arguments are exchanged. Note in particular that no disturbance remains as an input in the final vector field E because we have substituted the extreme possible values of the disturbance set W. We denote the solution for this embedding system at some time t from an initial point x hat using capital phi e. To state the main monotonicity property of this embedding system, we define a particular southeast partial order on a 2n dimensional state space as follows. A pair of points x and x hat is less than or equal to another pair y hat with respect to the southeast order if and only if x is less than or equal to y and y hat is less than or equal to x hat, where these inequalities are component-wise. It then follows that the embedding system is a monotone dynamical system with respect to this southeast order, and therefore the state update map phi e maintains a partial order relationship as shown in the green box. I want to pause briefly to highlight some historical context here. The particular form of the embedding function on this slide is closely related to a similar construction given in a 2006 paper by Enciso, Smith, and Sontag, referenced here on this slide. This basic approach also extends naturally to the discrete time formulation, although I won't cover the details of the discrete time form in this talk. In discrete time, this embedding system takes a form similar to that proposed in the 2006 paper by Hal Smith, below on this slide as well. But the basic idea of proposing such an embedding system is actually rather old. To quote Smith from his 2006 paper, the embedding method is repeatedly rediscovered and its implications are often underestimated. I would say that this sentiment applies to this talk, where I present some of our new results in this area, and I'm arguing that there is still plenty of room for further advancements in this idea. We can now reinterpret the monotonicity property of the embedding system in terms of reachable sets for the original dynamics. The basic fact on this slide is the backbone for the refined technical results I will present shortly. Given a hyperrectangle defined by lower points, say x underline, and an upper point, say x overline, denote by RF the reachable set of the system over some horizon t. That is, the set of all final states at time t given an initial condition within the initial hyperrectangular set defined by x underline and x overline, and any disturbance input taking values within the hyperrectangular set of allowed disturbance inputs. This reachable set is contained within the rectangle constructed as indicated from the corresponding trajectory of the embedding system. So in particular, the lower corner of the rectangle is given by the first n components of the embedding system trajectory, and the upper corner is given by the last n components of the trajectory. Again, this fact follows readily from the definition of the southeast order and the monotonicity property of the embedding system with respect to this order. So the striking thing to note here is that a single trajectory of the embedding system provides an over-approximation of the reachable set of the original mixed monotone system as a hyperrectangle. So we demonstrate this important property with an example. Consider the two-dimensional system without disturbance as shown on this slide. It can be verified that the function d, shown here, defined piecewise, constitutes a decomposition for the dynamics. Then, given a certain initial region, as shown in the left figure, we can over-approximate the true reachable set over a horizon of, say, t = 1, which is shown in dark blue, with a rectangle determined by a trajectory of the embedding system, as shown in light blue. The corresponding trajectory of the embedding system, projected to the x1, x1 hat plane, is shown in the right figure. Note that the trajectory of the embedding system evolves in a region on the upper diagonal of this plot. This is a general property of the embedding system since it maintains a partial order with respect to the southeast order, and therefore trajectories cannot cross this diagonal line. In fact, the embedding system has several interesting properties that we'll explore in a bit more detail. First, in the case where there are no disturbances, the embedding system exhibits a symmetry property whereby trajectories above and below the diagonal are symmetric. The diagonal itself reduces to 2 copies of the original dynamics, and this set is invariant. These properties lead, for example, to sufficient conditions for establishing global stability of an equilibrium point. This is a topic we have explored in the past in work studying certain network flow problems. When disturbances are present, these properties change. In the case of disturbances, the upper triangular set T, as defined here on this slide, is an invariant set, and it becomes the domain of primary interest for analyzing the original system. In particular, equilibria or periodic orbits in this set, as well as their stability properties, give rise to robustly invariant and attractive sets, as we'll formalize next. So we make these properties of the embedding system precise with the following theorem. If a point x star, x hat star, is within this upper triangular region T, and it is an equilibrium point for the embedding system, then the hyperrectangle defined by the point x star and x hat star is robustly invariant for the original dynamics. Moreover, if the equilibrium is asymptotically stable, then this invariant set is also an attractive set. This theorem is actually a corollary of a more general result presented in this below referenced CDC paper of ours that characterizes families of successively tighter robustly invariant sets. We demonstrate this theorem with a few examples. So in this first two-dimensional example with dynamics as given on the slide, there exists an equilibrium point of the decomposition function, which we omit due to space constraints. We are able to numerically determine the smallest robustly invariant set for these particular dynamics, as plotted here in the dark blue region, and we see that the rectangle defined by the equilibrium point in the embedding space does indeed contain this set, as guaranteed by our theorem. In the next example, we consider a particular two-species instantiation of the generalized Latka-Volterra model introduced at the beginning of the talk. The corresponding embedding system has an asymptotically stable equilibrium point. Therefore, the rectangle defined by the equilibrium point is robustly invariant and attractive. Moreover, the basin of attraction can be under-approximated by considering the basin of attraction for the equilibrium point in the embedding space. In these plots, we see the equilibrium point and a particular trajectory that converges to the equilibrium point projected to the x1 versus x1 hat space and the x2 versus x2 hat space in the embedding system. In this example, we show that other limiting behavior in the embedding space is possible. This four-dimensional system emits a limit cycle contained in the upper triangle of the embedding space, and this limit cycle implies a periodic rectangular set that over-approximates the reachable set, as seen in this animation. So in this animation, again, the dark blue region shows the true reachable set computed numerically over time, and the light blue set corresponds to an over-approximation of this reachable set computed from a periodic trajectory in the embedding space. In recent work submitted to CDC 2021, we've extended these basic results to allow for state-dependent disturbances. This is particularly relevant in learning-based systems where it is desired to learn some unmodeled component of the dynamics, which can be considered a disturbance input. We will not present these results in detail, but we'll demonstrate them with the following example of a multi-rotor aircraft confined to move in the plane, which will also appear later in the talk. Its dynamics are given by the following equations on this slide, where the states are vertical and horizontal position and roll angle and their derivatives. The inputs are thrust through the center of gravity and rolling moment. The disturbances W1 and W2 constitute an unmodeled wind field, assumed here to be a function only of vertical altitude. By modeling W1 and W2 as Gaussian processes and applying the mixed monotone systems theory presented thus far, we were able to obtain high probability state-dependent disturbance bounds that translate to high probability reachable set approximations. So as an example, consider the goal of reaching a target altitude of z equals 50 and then returning to the ground while remaining within safe horizontal bounds, while position measurements are assumed unavailable for feedback during this maneuver. A possible control strategy adjusts the roll angle to compensate for estimated wind force during a climb and descend maneuver. So in this animation on this slide, we see that if the wind force estimate is poor, as demonstrated in these top two plots, showing estimates and confidence bounds for W1 and W2 as a function of altitude z, then the reachable set becomes large and the trajectory becomes unsafe. So we see here that with poor wind estimates, the reachable set approximation becomes very large and violates the horizontal safety constraints. However, if additional wind measurements lead to better estimates, as shown in this case, then the multi-rotor is better able to compensate for the wind force. So here in these upper two plots on the right, we see the decreased uncertainty in the wind estimates. This will lead to smaller reachable set estimates and a safe trajectory, as we see in this animation. Notice that with better estimates of the winds, the multi-rotor aircraft is able to compensate for the estimated wind speeds by adjusting the roll angle throughout the maneuver, and the decreased uncertainty in the wind field also decreases the uncertainty in the reachable set estimation over time. Now that we have seen how the mixed monotonicity property is used to compute reachable sets and robustly invariant sets, we briefly address the problem of computing decomposition functions, which is an active area of research interest in our group. We first mention an important special case which provides a sufficient condition for computing decomposition functions. So, namely, if the off-diagonal entries of the Jacobian matrix del f del x are sign stable, so that means that these entries do not change sign as the state x and disturbance w vary, and in addition, del f del w is also sign stable, then a decomposition function is constructed from f by associating appropriately hatted variables when the sign of these entries is negative. This is in fact the construction that we used in the generalized Lotka-Volterra model at the beginning of the talk. Moreover, it has also been shown that this general approach extends beyond sign stability to the case when the entries are either upper or lower bounded. This was shown in the paper on the bottom of this slide. Besides this special case, some classes of systems have been shown to be mixed monotone by appealing to the particular structure of the dynamics and to domain knowledge particular to the problem at hand. More recently, our group has made progress on establishing general conditions for existence and construction of decomposition functions. In a recent paper, we have shown that any system with Lipschitz vector field actually admits a Lipschitz decomposition function d given by the equation shown on this slide. So if we unpack this equation a bit, we see that given a point x and another point x hat, each component of the decomposition function is assigned the minimum or maximum value of the corresponding component of the vector field evaluated over an appropriate face of the hyperrectangle defined by the corners x and x hat. Whether this optimization problem is min or max depends on whether x and x hats are the lower and upper corners of the rectangle or vice versa. Not only does this particular construction provide some decomposition function for the dynamics, it actually provides the tightest possible decomposition function, where tightest means that the entries of the decomposition function are ordered with respect to the entries of any other decomposition function. This fact, in turn, implies that this particular decomposition function provides the tightest approximations of reachable sets and robustly invariant sets using the mixed monotone theory presented earlier in the talk. This recent result answers an important question about mixed monotonicity, namely, how general is this mixed monotone property? This theorem tells us that the property is in fact very general, and its usefulness depends critically on availability of a tractable decomposition function. Note that while this theorem provides explicitly what is in some sense the best decomposition function, it is given in terms of an optimization problem to be solved for every set of arguments, and therefore it's generally not computationally tractable. However, this result has led us to show that in some cases, such as systems with polynomial vector fields, this decomposition function can be given in closed form as a piecewise defined polynomial decomposition function. Moreover, insights from this result tell us how we can construct alternative decomposition functions that may not be the tightest, but are easier to evaluate because, for example, they are defined with fewer pieces in this piecewise definition. We are also finding other cases where augmenting the original state space can actually lead to better decomposition functions. And in general, this is an active area of research for us. I also want to note that this result on this slide for continuous time systems was preceded by a related result for discrete time systems presented at CDC in 2019, referenced below. I want to now return to an example from earlier in the talk to briefly demonstrate the importance of using a good decomposition function. Recall that for this particular system shown on this slide, we provided a particular decomposition function defined piecewise as shown again on this slide. In fact, this was the tightest decomposition function, and therefore it satisfies the optimization-based condition given on the previous slide. For this example, the entries of the Jacobian matrix are actually not bounded, and therefore the traditional sign stability method of obtaining a decomposition function does not apply, at least not across the entire domain for the system. However, it is possible to restrict consideration to a compact subset of R2, and then we can use bounds of the Jacobian over that subset. However, this method can quickly lead to poor reachable set estimates. In this plot, we show the reachable set of the system from the initial set as shown for a horizon of t equals 1/4. The approximation of this set using the tightest decomposition function is seen to closely approximate the true set, while an alternative approximation obtained using a decomposition function constructed from the bounded Jacobian matrix is substantially worse. Okay, in the last part of this talk, I will show how we are using mixed monotone systems theory to guarantee safe autonomy by including reachable set computations in the control loop. I won't go into the technical details too much, although there is some rich theory here, particularly pertaining to novel constructions of control barrier functions. Instead, I'll just try to give a high-level overview of our general approach and show some examples. Our approach to safe autonomy can be classified in the context of runtime assurance mechanisms, which broadly refers to control architectures that aim to prevent unsafe control actions at runtime. This is generally achieved by partitioning the state space into a safe and an unsafe region. And whenever a control action has the potential to move the system state into the unsafe region, the runtime assurance mechanism intervenes and alters the control inputs. So while this approach is logical, there are potentially many challenges to realizing such a scheme in practice. One notable challenge when working with dynamical systems is that just because a particular state is not in the unsafe region does not mean it is inherently a safe state. So more precisely, if we were to call the complement of the unsafe set the allowable region, as shown in the figure, there will be some states that are allowable but inevitably lead to the unsafe set. So a canonical example of this is a vehicle that is traveling too fast to avoid collision with some obstacle in its path, no matter what evasive maneuver is attempted by the vehicle. So the appropriate control theoretic solution to this is to compute a subset of the allowable set that can in fact be guaranteed safe. Ideally, one would want to find the largest such set, and this set is sometimes called the viability kernel for the system. But in general, pre-computing such sets can be computationally challenging for many of the same reasons that computing exact reachable sets is challenging. So a solution that we consider is to instead ensure that the system is able to reach an a priori verified region that is in fact robustly invariant with respect to some backup controller. So this set is generally a conservative safe region, and we don't want to restrict the system only to this verified set. So to achieve that, we allow the system to evolve beyond the verified set by making sure that this particular backup control strategy is always able to reach the verified set. So this whole concept is illustrated in this figure where we show this a priori verified safe set, and we show trajectories that are able to reach this safe set. In the setting when a disturbance input is present in the system dynamics, we therefore need to compute the reachable set of the system under the backup control policy and not just a single trajectory in order to ensure that the reachable set under any disturbance input becomes contained within the safe subset. So in our recent work, what we've done is we've proposed an approach that uses mixed monotonicity to compute the reachable sets, and then we use control barrier functions in a novel way to ensure that the reachable set becomes contained in the verified subset. To provide an abbreviated glance at the technical details that we developed in this line of work, suppose that a conservative subset, this conservative verified subset, is defined as the super zero level set of some function psi of x. We can then define a control barrier function h of x implicitly as the maximum over some a priori time horizon t of the minimum value attained by psi over the reachable set of the system computed from the current state x under the backup control policy. The mixed monotone approach makes it so that h of x can be efficiently evaluated by considering only the corners of the reachable set under some mild technical assumptions on the function psi, and this also enables an efficient method for computing the gradient of h via sensitivity analysis of the embedding system. This gradient is required when using the control barrier function to formulate an optimization problem solved online to compute safe control inputs. So we now demonstrate this approach on a few examples. The first example is an academic example of a 3-vehicle platoon resulting in a 5-dimensional state space with disturbances entering additively in the velocity dynamics of each vehicle. The backup controller that we consider is a nonlinear spring force between the vehicles. A conservative, robustly invariant ellipsoid is computed from linearizing the dynamics, and the proposed control architecture keeps the system within reach of this invariant ellipsoid at all times. This is demonstrated in this following animation. So in the animation, we see that the trajectory follows the nominal trajectory initially, but then it deviates from the nominal trajectory to ensure that the reachable set, shown as the lightly shaded blue region, blue rectangle here, remains within reach of the safe invariant set, which is a green ellipsoid shown here. The green ellipsoid changes over time because it is projected as a higher dimensional ellipsoid projected to the displacement states in this plot. Our next example considers 2 interacting multirotors where we use the same multi-rotor model described earlier in the talk. The resulting overall system has 10 state spaces, 10 states, because we replace the 4 positional states with 2 relative displacement states. And the system includes disturbances as shown on this slide. The allowable set for the coupled system is taken to be a specified ball around a nominal displacement. So in the 10-dimensional state space, this safe set, this allowable set, becomes a cylindrical set for the dynamics. This system has an undefined relative degree at some points along the boundary of this cylindrical allowable set. This means we cannot simply use the allowable set as a standard control barrier function, motivating the use of our runtime assurance approach. For this example, we demonstrate our algorithm on an embedded hardware-in-the-loop experiment. Our algorithm is implemented in C++ on a Jetson Nano single-board computer, as it would be in a full hardware experiment. We use Gazebo for the physics engine, and we incorporate our controller in the PX4 autopilot stack. Communication for this experiment is handled with ROS. This slide shows a snapshot from the experiment that I'll show shortly. We consider a nonlinear spring-type backup controller, again, as we did in the previous example, between the two multirotors, and we compute a robustly invariant verified region by linearizing the dynamics at the equilibrium points. The verified region is an ellipsoid in the 10-dimensional state space, and its projection in the displacement coordinates is shown in green. The allowable region is shown in purple. As indicated in this snapshot, our algorithm keeps the system states within reach of the verified region. The bottom plot shows the result when a nominal controller commands both multirotors to the same position, in this case at the point 0,2. Without our proposed runtime assurance mechanism, the multirotor trajectories would collide. With our proposed controller, the multirotor trajectories maintain a safe distance. In this video, we see how our proposed controller avoids collision. So in the video, the red quadrotors are executing an unsafe maneuver without our runtime mechanism and would collide. The other two multirotors are running our runtime assurance mechanism and avoid collision. Now, this video might seem rather straightforward, but what I really want to emphasize here is that our algorithm is computing reachable sets of the 10-dimensional system in the control loop in real time in order to ensure that safety violation does not occur. So to elaborate on this point a bit more, in this slide, we plot the nominal versus applied thrusts to each multirotor. The nominal thrust would lead to safety violation, while the applied thrust keeps the multirotors safe from collision. As in the previous example, we see that for a while, in this case, it's the first half of a second, the applied thrust and the nominal thrust basically coincide. But then the runtime assurance algorithm intervenes and adjusts the thrusts to avoid collision. Finally, what I really want to emphasize in this example is how quickly we are able to run this algorithm in the loop on embedded hardware. This table demonstrates computation times for the key elements of our algorithm. We over-approximate reachable sets of the system in about 4 milliseconds by computing a single trajectory of the embedding system. Next, we compute the barrier function h by considering if and when the reachable set becomes contained within the verified subset. This computation takes about 3.5 milliseconds, and a byproduct of this computation leads to computing the gradients of the barrier function h in about an extra 2 milliseconds. Solving the resulting quadratic program for the control barrier function takes up to about 1 millisecond, and the average total computation time for all of these processes is about 10 milliseconds. So we are able to include reachable set computations in the control loop of a 10-dimensional system on embedded hardware at about 100 hertz. So I believe this sort of demonstration really opens up new avenues for ensuring safety in such highly dynamic systems that require fast control loops by embedding reachable set computations in the control loop. In this case study, we consider a spacecraft with 3 degrees of rotational freedom. We modeled a system with 7 states consisting of a 4-dimensional quaternion and 3 angular velocity dimensions. Using a quaternion representation for the rotational state allows for a closed form tight decomposition function for the dynamics. We implement our runtime safety assurance approach on the Astros experimental platform at Georgia Tech. In the first experiment, the goal is to keep the spacecraft orientation so that the angle between the inertial frame z-axis and the spacecraft z-axis is within 23 degrees. We compute reachable set approximations over a 15-second horizon with a controller update rate of 10 hertz. In this case study, instead of using the barrier function formulation previously discussed, we use a slightly different methodology whereby the controller switches to the backup controller for a period of time if the spacecraft reachable set is too close to the safety bounds. In this video, we see the spacecraft hardware in the upper left. A human controls the spacecraft with a joystick shown in the lower left. but our runtime assurance algorithm will take over control from the human if safety violation is imminent. The upper right plot shows the spacecraft orientation along the safe 23-degree cone, and the lower plot shows the reachable set estimation of the angle between the reference frame and the spacecraft z-axes over time. The reachable set approximation turns green during periods when the runtime assurance controller is active, and we see in the video that the spacecraft remains within the safety bounds. In this second experiment, the goal is to keep the spacecraft orientation away from a 16-degree cone centered at the inertial x-axis. For example, the spacecraft might have sensitive equipment that cannot be pointed directly at the sun. In the video, we see that the spacecraft follows a nominal figure-8 trajectory. At all times, we consider a backup controller that would orient the spacecraft 180 degrees away from the unsafe cone along the negative x-axis. And we compute the reachable set along with this backup trajectory using a trajectory of the embedding system. When the trajectory gets close to this forbidden 16-degree cone, then the computed backup reachable set can no longer guarantee safety, and the runtime assurance control activates thrusters, which you can see in the simulation, to execute the backup control maneuver for a period of time to maintain safety. I also want to briefly mention ongoing work in which we apply our runtime assurance methods for safe watercraft control. We are collaborating with an industry partner to implement these ideas for obstacle avoidance on a twin-engine boat. While this is still ongoing work and we haven't completed these results yet, this video shows some of our results in simulation, and we hope to have implementation results later this summer. Okay, I want to wrap up with some concluding thoughts. A main thesis of this talk is that fast methods for computing reachable sets are needed in emerging domains like formal methods for control systems and runtime safety assurance. In these cases, speed is often more important than exactness. I believe that mixed monotonicity is a promising approach in this area because a single trajectory in the embedding space provides hyperrectangular over approximations of reachable sets, allowing for fast computation of these sets. And these approaches are able to accommodate disturbances in a natural way. I also want to point out that this approach seems to be maturing quickly through our work and the work of others, and has been shown to be practical for algorithm development with demonstrations on a growing list of physical platforms. And finally, of course, it's a great pleasure to be able to thank a few folks who have made this work possible. First and foremost, my students are the enabling force behind all of these ideas and experiments. The recent papers below are the result of my hardworking students, and I encourage you to check them out. This work was funded in part by the Air Force Office of Scientific Research, and I very much want to thank Fred Levy for his continued support. Finally, this work certainly would not have been possible without the kind and enthusiastic encouragement from the late Kishan Beheti at NSF. I know many of us have had the pleasure of knowing Kishan, and some of you have known him for quite a while, and I want to acknowledge the tremendous support he provided during this early part of my career. He will certainly be greatly missed. And that concludes my talk. Thank you very much for your attention. I'll be happy to take any questions now.